This is Holy Cross Component 2 mock, and this is mock number 1. And we're on to question 6. The diagram shows a piece of double-stranded circular DNA found in a bacterial cell in addition to the bacterial chromosome. So here's a bacterial cell with a cell wall, maybe a flagellum. Bacterial chromosome will often be circular in nature, and then these are little circular double-stranded DNA. So this is what we're talking about. One of those. The general name given to this is plasmid. That's an okay start. And it's got a gene for antibiotic resistance. So antibiotics like penicillin, streptomycin, they are produced by fungi to kill prokaryotes and to kill bacteria, and that's why your doctor might give them for a bacterial infection, but not a cold or flu, because that's viruses. It won't have any effect there. So there's the gene for antibiotic resistance. That's quite often how bacteria spread these around on these plasmids. The circular DNA acts as a vector. Describe its role in production of insulin by genetic engineering. So a vector will carry a gene for insulin. So if we can put this gene for insulin in here, then this plasmid will carry that to where we're going to put it back into a bacterium. So we take it out, put in our insulin gene, put it back into the bacteria, and then when the bacteria grows, it will produce insulin. So it carries the insulin gene. And where are we going to put it? We're going to put it back in to the bacterium, so that then the bacterium will express that gene and produce insulin. So it carries the insulin gene into the bacterium. Pretty straightforward so far. REST1 is a restriction endonuclease that recognizes the base sequence that. So restriction endonucleases, they cut DNA. And this one, it says it cuts between guanine and adenine, between G and A, so it cuts there and G and A there, so that's how that cut would be. Using this information, describe how restriction enzymes give rise to sticky ends. So this cuts both strands of DNA, so cuts both strands of DNA, and the key thing is it's a staggered cut. That leaves unpaired. We'll have 4 unpaired bases. So staggered cut, which are leaving unpaired bases. That's why they're sticky, because they could very easily form hydrogen bonds again with their complementary base. Describe the role. I don't know why the role is in on this typing. You've got a little hat on like a French law, the sticky ends. Well, what do sticky ends do? Well, they would join onto their complementary base. But we could use another DNA strand that's been cut in the same way by the same restriction endonuclease. So we can join other bits of DNA together to form kind of recombinant DNA. So these will join with complementary. So using our keywords there, complementary bases. Yeah. on other DNA fragments, like for example cutting out a gene or cutting another plasmid, for example plasmids. And we will mention something else that we need to do with sticky ends. We need to form these phosphodiesters, these main bonds between the bases with DNA ligase. So join with DNA ligase. So we'll get hydrogen bonds between the bases, but we'll get covalent bonds, strong bonds for the sugar phosphate backbone. Explain why the antibiotic gene is inserted into the circular DNA. Do they still really do this? Why not use fluorescent genes or something a bit less dangerous? However, this would act as a marker gene. I like to say marker gene. And so any bacteria that take up our insulin gene would also have this antibiotic resistance, so you could treat them with antibiotic, and the ones that survive have got our gene, which is great. So can identify bacteria that have taken up the plasmid with the insulin gene. The others are killed, and then you separate out the ones that you want and grow them and so on. Okay. DNA fingerprinting produces a DNA fingerprint that looks nothing like this. Blood sample. Oh dear me. This is kind of a year 7 diagram of genetic fingerprinting. Name the process. Well, you should have seen a demo of this in your laboratory sessions. So the process that produces this is electrophoresis, where you've got these fragments migrating, and the smallest fragments would go further through the gel. State who is likely to be the attacker. Well, we're comparing our attacker fragments. There we are. Okay, and so suspect 1 has got a couple in common. Suspect 2, all 6 in common. Suspect 3 has just 3 in common. So suspect 2 has got all 6 in common, whereas suspect 1 has just got 3. Suspect 3 has got 3. So suspect, more likely to be suspect 2. So suspect 2, bang to rights, lock them up. And explain how you reached this conclusion. Well, suspect 2, now all six bars, fragments, that sort of thing, bands would be a better word, wouldn't it? Bands match the attacker. Suspects 1 and 3 have only 3 matches. State 1, other use of genetic fingerprinting, things like paternity cases, so we would have a child and we'd have 3 possible fathers all denying everything. Which one of them is going to have to pay up? So paternity cases. The other And you could have all sorts of other, you know, things like, you know, using archaeology and all sorts of different things. Taxonomy, classification, which leads us nicely on to the next question.